Hey, welcome back for AP Chemistry. You're here with Mrs. Mays, and now we're going to be looking at polyprotic acids. We're going to take a closer look at how to handle a situation where more than one hydrogen dissociates from the acid. Here's an example. We need to calculate the concentration of all the ions in a solution of 1 molar arsenic acid, which is H3ASO4. So we have a triprotic acid, and I'm going to need more space. Alright, so first let's write the dissociation reactions for each of these. In Ka1, this is the situation where the first acidic hydrogen dissociates from arsenic acid. So I get a hydrogen ion, and I'm left with 2 hydrogen, and I'm left with 2 hydrogen atoms still attached to the arsenate. So this would be what? Dihydrogen arsenate, it looks like. The next dissociation describes when that conjugate base, H2ASO4, then loses one of its hydrogens. That's not a 2- charge, that's just a 1- charge. Let's fix that. -1, there we go, that's better. So one of the hydrogens comes away, and I'm left with only 1 acidic hydrogen still attached. Now I have a 2- charge. And then of course the third dissociation is when that last hydrogen comes away. So HASO4 that has a 2- charge loses that last hydrogen, and we don't have any more to lose. So I get the arsenate ion without any hydrogens attached. So that's the dissociations. But the question says calculate the concentration of all the ions in the solution. So what are all of the ions? Well, I have H3ASO4, that's part of our solution. I have hydrogen ions from 3 different sources. I have H2ASO4, HASO4, and ASO4 3-. So I have all of these ions to keep track of. I'm going to use a Rice table to tell how many ions we're dealing with in the first place. So let's start with the first reaction. I'll call it R1, that corresponds to my first dissociation, Ka1. So H3ASO4 reacts with water to form hydrogen ions, or hydronium ions, whichever way you want to write it, and the dihydrogen arsenate ion. My initial concentration is 1 molar, and of course for my products I don't have any yet. The change is that I will lose some of my arsenic acid, and as I lose those, I also form hydrogen ions and dihydrogen arsenate ions. So I get 1 - X, X, and X. My equilibrium constant, Ka, is represented by products over reactants. So I can write my expression with hydrogen on top and my conjugate base, and then the acid on the bottom. That's also equal to, with my equilibrium from the Rice table, X times X over 1 - X. And that has a value of 5 times 10 to the -3. So we need to solve for X. And I have a small enough Ka that I can use the small x assumption here and say, well, that's not going to change anything when I subtract 1. When I subtract a really small number from 1, it doesn't change it. So x squared equals 5 times 10 to the -3, square root both sides, and we find the value of x 0.071. And that gives us the molar concentration for hydrogen ions and for dihydrogen arsenate ions. I'm going to be using that in the next part of my problem because now I have to do the second dissociation. So in the second dissociation, we'll call that R2. I start with dihydrogen arsenate, and I take away another hydrogen. And I'm left with hydrogen arsenate that has a 2- charge. Note what we do with the initial concentrations. I started with 1 molar arsenic acid. My X from that dissociation was 0.071. X gives me the value of both the hydrogen ions that I have in the beginning and also the dihydrogen arsenate ions that I have in the beginning. And of course, before this one dissociates, I don't have any hydrogen arsenate. But then I lose some of this, and as I do, I gain 1 mole of hydrogen ions and 1 mole of hydrogen arsenate. So then I end up in equilibrium with 0.071 minus X, 0.071 plus X, and X. So now let's write the Ka for the second dissociation. Products over reactants, just like before. So I have the conjugate base on top and the acid on the bottom. And that's my second dissociation. This one up here was my first dissociation. And of course, with my equilibrium, so I get X times 0.071 plus X, those are on top, and then 0.071 minus X is on the bottom, which corresponds to my Ka of, my Ka2, 8 times 10 to the minus 8. So, again, I have a small Ka. We can say that these X's here are not going to change the value of the 0.071. So X is going to be equal to, and these cancel away, 8 times 10 to the minus 8 molar. So we'll add that to the hydrogen we already had, and we'll use that as our starting value of the hydrogen arsenate ion for the third dissociation. So in my third reaction, we get the hydrogen arsenate, drop in the last hydrogen, and I get the arsenate ion with no hydrogens left. So my initial concentration of hydrogen arsenate is 8 times 10 to the minus 8 molar, whereas my hydrogen now is building up. I have 0.071 plus X, and then of course arsenate is none yet because they haven't been created. So I lose some of my reactants and I form an equal molar amount of my products. So I get 8 times 10 to the minus 8 minus X at equilibrium, and then for hydrogen I have 0.071 plus X from my second reaction and then X from my third reaction, and for arsenate I have just the X from my third reaction. So now I have to keep careful track of what's what here, don't I? So this one is X from the second. Alright, we are almost there. Now let's write the equilibrium expression for the third dissociation. I get the arsenate ion times the hydrogen ion, all divided by the hydrogen arsenate concentration. So when I put my equilibrium values in, I get on top 0.071 plus my second X and my third X concentrations of both products, right? And then down here I have 8 times 10 to the minus 8 minus. All right, and we set that equal to the value of my third dissociation constant, 6 times 10 to the minus 10. So then I use my solver or my small x assumption, which is easy to do. These are so small they don't even count. So x is going to be equal to, let's see, multiply that one across and that one. So I get x is equal to 6.7 times 10 to the negative 16 molar. So now let's summarize the concentration of all the ions in our solution. We had a lot to keep track of here, but I'm still going to have arsenic acid in its undissociated form to quite a large extent, actually. We started with a 1 molar solution, and I lost some x from my first dissociation. So that was 1 minus 0.071, and that gives me 0.929 molar. The dihydrogen arsenate ion is also around in an appreciable concentration. I keep wanting to put that as a 2 minus. It's just a 1 minus. So that was 0.071, and then some of it dissociated in our second dissociation. But that second number was 8 times 10 to the minus 8, so it's like 0.070999992, which is, we don't have enough sig figs, so we call that 0.071 molar. That's all we get to keep. And then I have hydrogen arsenate. That's the one that's a 2 minus. And that was 8 times 10 to the minus 8 molar, but we lost some of it in the third dissociation. But remember, the third dissociation, x was like 10 to the minus 16. So this is like ridiculous. Look, here's what I get. 7.999999933. So really, we're still going to call it 8 times 10 to the minus 8 molar. And then we have the arsenate ion, which was formed in the very end. It's just equal to the x from our third dissociation. So that was 6.7 times 10 to the negative 16 molar. And then here's the one that's going to give us our pH value. Hydronium ion, which in this reaction I just called hydrogen ion, same thing. And that's going to be equal to the 0.071 plus 8 times 10 to the minus 8 plus 6.7 times 10 to the negative 16. And since I don't have enough sig figs to worry about these two values, we just call it 0.071. Basically, what do I get? Yeah, 0.071. We said we could use the small x assumption, and we were right, because it doesn't really change our sig figs. So the pH we can find now by taking the negative log of the hydrogen ion concentration, or the negative log of 0.071. And that gives us a pH of 1.1. So just because it's not a strong acid doesn't mean that its pH is going to be something close to 7. Strong acid or weak acid, that's not the point. Look at all of these sources for hydrogen ions in our solution. Of course, we get the most from the first dissociation because that hydrogen is the easiest to pull away.